Hello everyone, my name is Milijana Surbatovich, and today I'll be talking about our work in developing a formal framework to reason about intermittent computing systems that I did together with my advisors, Lucia and Limin Jia. Batteryless energy-harvesting devices are an emerging class of system that enable computing in inaccessible environments, such as space, in-body implants, or remote wildlife monitoring. This is because maintenance in these environments is expensive or even impossible. This makes batteries undesirable as they have to be replaced, but it also makes it imperative that programs execute correctly, as buggy software or firmware will be difficult to patch or may even make the device useless. So batteryless energy harvesting devices are a good fit for these environments because they instead harvest and store energy into a capacitor, but unfortunately it becomes much more difficult to reason about if a program will execute correctly, and I'll explain why on the next few slides. How these devices work is that they consist of a hardware platform, an energy buffer, which is that capacitor, and a harvester, such as a solar panel that could harvest energy from the sun. As energy is available, the device will charge, powering on when the buffer is full. The device will operate until access to the energy source is removed, such as a cloud going in front of the sun, and the buffer drains. At this point, the device powers off at an arbitrary program location for an arbitrary period of time. Any volatile state clears, which typically includes the program counter and registers, but persistent state remains. The device remains off until energy becomes available again, repeating this cycle. Now, without runtime support, programs will not execute correctly. For starts, since the program counter and register is clear on power failure, to make progress, the runtime must save the execution context at checkpoints. The program will then execute until power fails. On reboot, the program will continue executing from the last saved checkpoint instead of the beginning of the program, re-executing this partially executed section B. Now, unfortunately, this re-execution can cause bugs. One problem, which is largely solved by existing systems, happens if there is a write after read dependent, such as when X reads Y and then Y is set to 5. Re-executing this block introduces incorrect data flow, and X will read the new value of Y instead of the original. So to be correct, the checkpoint needs to back up the original value of Y as part of that saved execution context. Now, one system that does this that I'll refer to repeatedly throughout the talk is called Alpaca, so it adds any variables with a write after read dependence to the saved execution context, and there are many such systems that do this. One problem that existing systems largely don't handle correctly is caused by repeating input operations. Consider this program that reads from a sensor and then branches on that value, setting Y to 1. The value returned by the sensor could be different on re-execution, causing the branch to not be taken, and Z to be set to 1 as well. So now it's incorrect behavior to have both these variables set. Now, last year at OOPSLA, we presented a paper that provided a bug finding tool, IBIS, that can detect and report instances of this problem, but it does not provide a correct runtime system or a formal specification of correct behavior. So because there is no formal spec in existing work, this can make systems subtly incorrect, such as with the problems caused by repeating input operations. Now, our correctness definitions and theorems in this work address both write after read and RIO problems, which no existing work has done. So, making programs execute correctly on intermittent power is challenging, and there is a gap in existing work. I'll now talk about our correctness definition and the invariants to reason about if an intermittent execution is correct, which bridge that gap. The intuition for correctness is that continuous executions are the specification of correct program behavior. This means that a given intermittent execution is correct if there is some equivalent continuous execution. And now for a program to always execute correctly, this must be true for all such intermittent executions. Now, the traces don't have to be the same, but rather equivalent. And equivalence means that memory reads, and the memory state at each checkpoint or the end of the program match that of some continuous execution. And there's two main challenges to reasoning about equivalence. The first is that rebooting only reverts some values, so the restored state isn't the same as was at the checkpoint. Second, inputs can cause the program to take a different path on re-execution. Now, these behaviors make equivalence difficult to reason about, since even a correct intermittent execution will have different memory than any continuous execution at many points. I'll now show how with a concrete example. Consider this little program. All variables are in non-volatile memory. The program first takes a checkpoint, then it reads from a temperature sensor, branching on the value, setting x and y if the branch is taken, otherwise setting x and z. I'll now step through an execution with time going downwards. The program starts by taking the checkpoint, saving the values of y and z. The program then reads the input at time 1. The value is 5 and the branch is taken, updating x and y before power fails. On reboot, the system reverts y and z to the saved values. Note that t and x are still different even after the checkpoint is restored. Considering these differences, let's see if there is a continuous execution on the right from the starting state that will have the same observations and final state. At time 8, the input is re-executed, giving a different value that causes the branch to be not taken. At time 9, both executions read the same value for z, so there is observational equivalence, and at time 10, z is updated to 8 on both executions. So the intermittent execution was correct, even though memory was different for half the trace. So the key question for reasoning about memory consistency on an intermittent execution is how different can memory get that the differences will still resolve? So the correctness definition is that any intermittent execution must be equivalent to some continuous execution. Differences in memory make this difficult to reason about, however, so the key piece of our formalism is two memory relations that define what differences are acceptable. The intuition is that to be correct, any differences in memory must resolve on re-execution. This means that after a power failing in reboot, all different locations must be written to before being read to give observational equivalence, and moreover, the written values must be the same as in a continuous execution so that no differences remain by the end. Now, checkpointed variables will be reverted to their original values, so easily resolving differences after reboot. Any non-checkpointed variables, however, must be in some set that won't cause inconsistencies on re-execution. So we define this set as the must first write set. Must write variables that have no preceding read, so they're first writes. This set is important because any execution will write to these variables before reading them. In the example program, t and x are in this set. We use this set to define two relations. The first describes the relation of the intermittent execution state at an arbitrary point to the initial continuous state. It says that differing locations must be in the must first write set or the checkpoint set. And this is because the checkpoint set is always reverted to the initial values, and all variables in the must first write set will be written to. Relation 2 deals with the two memories at the same execution points as in the final execution. It says that differing locations must be in the must first write set, and they cannot have been written to yet. As variables are written, the values must be the same. Now, as long as the intermittent execution state satisfies these two relations, we can prove that it's correct. So we can prove that an intermittent execution is correct if it satisfies the relations, but this is dependent on what is in the checkpoint set. For the relations to hold, all writes must be either must first writes or checkpointed. Now this is because must first writes, as well as read-only variables, will always be accessed consistently, but other variables must be checkpointed. Only checkpointing right after read variables, as many existing systems do, is insufficient, as this misses variables that are conditionally written because of inputs. To cover this difference, we define another set that must be checkpointed, the exclusive may-write set, and this is may-writes minus must-writes. The exclusive may-write set needs to include all variables that only may be written on an execution. Now, inputs are what causes re-executions to take different paths. Thus, the collection algorithm uses a static taint analysis to find input-dependent branches, and then collects the sets of variables written on each path. So in our example program, t, x, and y would be written if the branch is taken, and the program would write to t, x, and z if the branch is not taken. So t and x are written on all executions, so they're must writes, but y and z are exclusive may writes and must be checkpointed. Now, we call collecting the exclusive may write set from only input-dependent branches taint optimized EMW. Collecting from all branches is correct but conservative, as variables written on a path from a non-input dependent branch will be written on all executions and are actually must writes. Taint optimized EMW is correct but more precise. Now, defining EMW sets is the last piece we needed for our correctness theorem. Informally, it says that as long as all unsafe write after reads in EMW variables are in the checkpoint set, then an intermittent program will execute correctly. Now we can prove this using the memory relations, which will be satisfied with this checkpoint set of EMW plus write after reads. We implemented both versions of the collection algorithm, taint optimized in all branches in LLVM, and we added the compiler analysis to Alpaca, which already tracks write after reads. Now there's a lot more on the set collection and implementation in the paper. I'll now wrap up this talk with describing our evaluation. The goal of the evaluation is to show that modifying Alpaca with EMW sets is practically efficient. This means that there's low runtime overhead and also low programmer burden. The programmer shouldn't have to do all this reasoning about memory differences and exclusive may writes to know if the program will execute correctly. So we ran modified Alpaca on the benchmarks from prior work on real hardware under continuous power. This graph shows the normalized runtime. The y-axis is that runtime, and the x-axis are the names of the benchmarks. The benchmarks highlighted in pink are the ones that had input-dependent branches, so there were variables in the EMW set that needed to be backed up. Blue bars denote plain Alpaca, yellow bars denote Alpaca plus the all-branch EMW, and green bars denote Alpaca plus the taint optimized EMW. We can see that there was low mean overhead for both versions, but particularly for the taint optimized. The plain EMW frequently had higher runtime overhead because it adds spurious locations to the checkpoint. Now let's look at what programmer effort is needed to ensure that programs will execute correctly. Now, with plain Alpaca, programmers can use suggested heuristics or the bug finding tool from prior work to fix the programs, but they could still be incorrect as the bug finding tool isn't sound or the programmer could simply make a mistake. Alpaca with all branch EMW requires no effort, but it does have the higher overhead from adding spurious locations to the checkpoint. Taint optimized EMW, to use it, the programmers need to specify input functions to hook into the taint analysis, but there is extremely little overhead. So there's a lot more on everything in the paper, including using the framework to prove equivalence between various intermittent execution models, more details on the collection algorithms and implementation, as well as discussing how to apply the framework. Now, one application that I'll touch on is connecting it to related work in the fields of persistent memory modeling and crash consistency. Persistent memory modeling reasons primarily about differences in persist and execution order in multi-threaded executions or the actual persistency semantics of an ISA. Our target system is architecturally simple, but we must reason about non-deterministic inputs which are of particular importance for input-driven embedded systems. Crash consistency has very similar correctness definitions, but the existing frameworks or automation tools generally require the programmer to specify correctness invariants such as the ones we present for the first time here, those memory relations. So our framework is thus necessary for adapting frameworks and tools in these related fields to analyze future, more complex intermittent computing systems. So to summarize, intermittent computing systems need to be correct and reliable as they're envisioned to be deployed in inaccessible environments. We develop a framework and give a formal definition of correctness, and we apply this framework to reason about equivalence and develop a compiler analysis that will make existing systems correct. Thank you for listening.